Welcome to another deep dive. Today we're getting into the real cutting edge of AI, specifically multimodal large language models.
Yep.
Our focus is Ovis 2.5. It's a brand new MLLM from Alibaba Group.
That's right.
And our goal today is really to unpack the technical report that they put out, pull out the core ideas. What makes this one stand out? We want to understand how this model sees the visual world and then reasons about it. It seems to have some pretty new capabilities.
It's definitely an exciting area. MLLMs are moving incredibly fast. And, the core challenge has always been getting these models to truly understand both images and text.
Right.
Especially when the visual stuff is really dense or complex. It's more than just spotting objects. It's about deep comprehension, complex reasoning.
Yeah, that difference between just identifying something and actually understanding it. That seems key. So before Ovis 2.5, what were the specific hangups? What did older MLLMs, maybe even the earlier Ovis models, struggle with? The report mentioned issues with, I think it was deep reasoning or detailed analysis of visually dense content like complex charts.
That's a perfect place to start, actually, because Ovis 2.5 was really designed to tackle those exact problems head on. Think about it this way. Older models had generally two big hurdles with complex visuals.
Okay.
First, their vision systems, the vision front ends, were often pretty rigid.
Rigid how?
Well, they used fixed resolution encoders. So imagine trying to see a huge, detailed map, but you can only look through a tiny fixed size window.
Right, you have to scan around, piece it together.
Exactly. That's kind of what happened. These fixed resolution processors often force them into image tiling, chopping up the big image into smaller squares.
Oh, okay.
But when you do that, you lose things. Context gets lost, fine details might get messed up, and the overall structure, how different parts relate, that can be compromised.
Yeah, I can see that, especially for like a detailed chart or diagram.
Precisely. Where every little line and label matters. That's the first issue.
It's like trying to follow a story by only hearing random words. You miss the plot.
Good analogy. And the second main issue was about the reasoning training.
Okay.
Earlier models, they were often trained using a pretty linear chain of thought method. They could follow steps A to B to C to get an answer.
Right.
But they didn't really have what the report calls reflective, self-corrective supervision. Meaning, think of a student following a formula. If they make a small mistake halfway through, they might not notice. They don't have the built-in habit of stepping back, checking their work, and fixing it. They just keep going with the error.
So the models could generate steps, but not really evaluate if those steps made sense.
Pretty much. They weren't really trained to assess their own thinking process or, revise things if needed.
Okay, so Ovis 2.5 comes in to fix those two things.
Yeah.
Better visual understanding and stronger, more reflective reasoning. And there are two versions I saw.
Yes, that's right. There's Ovis 2.5-9B, the larger one, and then Ovis 2.5-2B, which is much smaller.
And the 2B.
That one follows their idea of small model, big performance. It's designed to be efficient, good for situations where you don't have massive computing power like running on a device.
Interesting.
But still aiming for really strong capabilities. It's pretty impressive, that balance.
Okay, let's unpack how they achieve this. Starting with the vision side. How does Ovis 2.5 avoid losing detail and messing up the overall picture? What's the tech?
So the core idea here is something they call native resolution perception.
Okay.
Instead of a standard vision transformer, a VIT, which usually takes a fixed size input, Ovis 2.5 uses a native resolution VIT. They call it NAVIT.
Native resolution, meaning it sees the image as it is.
Exactly. No more mandatory shrinking or chopping into tiles, that lossy tiling we talked about.
Yeah.
It processes images at their original native variable resolutions.
Okay. So a big high-res image stays big and high-res.
Essentially, yes. It preserves both the tiny fine-grained details and the global layout. So for that complex financial chart example, it can see the small print on the axis and the overall trend lines clearly.
That makes a huge difference.
It really does. They also did something else. They integrated rotary position embeddings, or ROPE.
ROPE?
Yeah, think of it like giving the vision system a better sense of spatial awareness. It helps the model understand where things are in the image relative to each other, especially with these high-res inputs. It just reinforces that spatial understanding.
So a clearer view and a better sense of space.
Got it. Now, the reasoning part, this deep reasoning capability and the thinking mode, how does that work? That sounds like a big step.
It really is. It's a move beyond just that simple linear chain of thought. They trained it using specific deep reasoning data.
Okay, what's special about that data?
Well, it doesn't just show the model step A, step B, step C. It also supervises these reflective processes like self-checking and revision.
So it teaches the model to check its own work.
Kind of, yeah. Like how humans learn. You solve a problem, maybe you pause, look back. Did I do that right? Is there another way? Did I miss something? If you spot an error, you correct it. So the model learns to generate intermediate steps to evaluate itself and then refine things.
Exactly. It learns to produce those intermediate steps to evaluate its own reasoning and refine conclusions when necessary. It's a shift from just giving an answer to understanding how it got there.
That's powerful.
And then there's that optional thinking mode you mentioned.
Right, at inference time.
Yeah. So the user can choose. If you have a really tough problem, you can basically tell Ovis 2.5, okay, take a bit longer on this one.
And it uses that extra time, too.
To run through more of those internal self-checking and revision steps. So you trade a little bit of speed, a bit more latency, for potentially much higher accuracy on those complex, nuanced tasks.
That's a smart feature. User choice.
And to make all this reasoning really hum, they also upgraded the core language model, the LLM backbone. They moved from Qwen 2.5 to Qwen 3, which apparently has better deep reasoning abilities itself.
Okay, that makes sense. So with all this new tech for vision and reasoning, how do they actually train this thing? It sounds complex.
It was definitely involved, but they focused hard on efficiency. They call it high-efficiency training. It's built around this really structured 5-phase curriculum.
Like a school program for the AI.
Sort of. It progressively builds the model from foundational perception to advanced reasoning. Starts with basic visual understanding, then connects images and text, then learns to follow instructions, and finally it uses advanced techniques like reinforcement learning, DPO and GRPO to really fine-tune its abilities and alignment.
So it learns step by step, not just thrown in.
Right. And the infrastructure behind it is pretty neat, too. They use things like multimodal data packing.
Data packing.
Yeah, optimizing how images and text are fed in together to minimize wasted computation, keep things balanced. And they used a hybrid parallelism framework.
Okay, that sounds technical.
It is, but think of it like efficiently splitting up the massive training job across many processors using different strategies. Data parallelism, tensor parallelism, context parallelism, all working together.
And the result?
The result was a big speedup. They reported a 3-4-head end-to-end speedup in training time, which is pretty significant.
Wow.
And underneath it all, the basic architecture still has familiar parts. A visual tokenizer to turn images into visual words, embedding table to manage those and link them to language, and the main LLM doing the heavy lifting on understanding and response generation.
Okay, so super sophisticated training, clever architecture, but the proof is in the pudding, right?
Yeah.
How does Ovis 2.5 actually perform? Does it live up to the hype on benchmarks?
Well, the results they shared are certainly strong. On the OpenCompass multimodal leaderboard, that's a pretty well-respected benchmark suite. The Ovis 2.5-9B model hit an average score of 78.3.
And how does that compare?
That sets a new state-of-the-art among open-source MLLMs in the sub-40B parameter range. That's a very competitive space.
Okay, SOTA in its class. What about the smaller one?
The Ovis 2.5-2B, it scored 73.9, which also sets a new state-of-the-art for models of that size. And both are big jumps from their previous model, Ovis 2.5-9B. So yeah, the new techniques seem to have really delivered performance gains.
Those numbers are definitely impressive, but can we make it more concrete? Where does Ovis 2.5 really flex its muscles? Can you give us examples of what this better perception and reasoning actually looks like in practice?
Absolutely. Let's break it down by task type. Take multimodal reasoning, especially with math and visuals.
Okay.
It apparently achieved the top rank on benchmarks like Math Vista and Waymath. Think about something like that toothpick problem they showed.
Right, where you have patterns made of toothpicks.
Yeah. Ovis 2.5 didn't just spit out the answer. It showed its work, step by step. Calculating the toothpicks for each stage, figuring out the pattern, then applying it. Or like a geometry problem with concentric circles in a diagram. It could lay out the theorems, the algebra, the steps to find the area.
So it shows its reasoning.
Clearly. And it also performed well on general academic reasoning, tackling college-level questions across different subjects. Quite versatile.
That step-by-step clarity is a big deal. Okay, what about reading text in images? OCR and charts?
Ah, yes, OCR and chart analysis. Here, it's not just beating other open-source models. The report claims it outperforms the proprietary GPT-4o model on OCR Bench v2.
Outperforms GPT-4o.
Wow, on that specific benchmark, yes. which suggests its ability to pull text accurately from images is top-notch.
Like reading a label.
Exactly. Give it a nutrition label, it can grab the calorie count, the fat grams, even from dense text, or take a shipping document. It can correctly pair the sender's address with the recipient's.
And chart.
Superior performance on Chart QA Pro. It can do things like a conditional search, find Senegal on a height mortality chart based on reading both axes, or even compare things within a chart, like figuring out which Christmas cookie recipe needs the most sugar from a visual flowchart of recipes.
So it's understanding the data represented visually.
And manipulating it. The report even showed it doing multi-step analysis across different chart panels, like finding U.S. states matching complex criteria based on multiple graphs.
That's impressive. What about visual grounding? Pointing things out in images.
Right, visual grounding. It hit a state-of-the-art average score of 90.1, and it particularly shines on a tougher dataset called RefCoCog.
What makes that one tough?
It involves complex descriptions of non-salient objects.
Yeah.
So not just find the dog, but maybe find the small red fire hydrant partially hidden behind the green bench.
Ah, tricky descriptions.
Exactly. And Ovis 2.5 seems very good at this. It can precisely locate an airplane way up in the sky or find the green tent in the middle of a busy campsite photo and give you the exact bounding box coordinates. Really precise localization.
That precision is key. Okay, last area, multiple images or videos.
Yeah, multi-image and video understanding. It shows superior cross-image reasoning. For instance, it can look at several paintings and recognize the art style, figuring out which ones share the same style as a reference image. That requires understanding abstract visual qualities.
Not just objects.
Right. And for videos, it shows strong and consistent performance. It can, say, describe the collision process of a blue sphere, detailing a sequence of events, or watch a video of a concert and give a detailed summary detailing video content of a musical performance. Who's playing what? What's happening? It's analyzing dynamic scenes over time.
Okay, it really does sound like Ovis 2.5 is a significant step forward. Handling complex visuals natively, that reflective reasoning, it really sets a new bar for MLLMs.
It seems to, yes. It's a tangible move towards AI that's more capable, maybe more aware in how it processes information, especially visually rich information. It brings us a bit closer to AI that can genuinely understand and interact with the visual world more deeply.
And this definitely raises an important question maybe for you, our listener, to think about. As these AI models get so much better at seeing and understanding complex visuals and even correcting their own reasoning, how might that change the way you interact with data? How might it change how you solve problems, especially when you're dealing with intricate visual information like diagrams, charts, or detailed images? Something to consider. Thank you for joining us on this deep dive